Hi, my name is Zimisha. I would like to present our work adapting fine-grained crossfield localization to areas without fine-grained shoes. The task of fine-grained crossfield localization is to estimate the location of a ground-level image on an area image that covers the local surrounding. State-of-the-art methods address fine-grained crossfield localization as supervised learning, namely deep models are trained with accurate location data as ground truth. Those methods perform well when the test images are collected from the same area as the training images. However, when the target area is in another city, state-of-the-art directly deploys the model in a new area, and because of the domain gap between training and test areas, this direct generalization results in inaccurate localization. In practice, it's infeasible to collect accurate location data to retrain or fine-tune the model in every target city. Instead, we highlight that connecting images with noisy location data is easy, for example, using phones and their built-in GPS. Our goal is then to leverage the noisy data to adapt the model to new target areas. Let's start with some observations. State-of-the-art methods predict heat maps for localization. As shown on the right, the red color on the area image indicates the localization probability. The darker the color, the higher the probability. The predicted location is a peak of the distribution. When generalizing to new areas, models' prediction becomes more uncertain. Those uncertainty can result in small positional noise, for example, the predicted location being a bit off from the ground truth, or large outliers, as shown in the image, the predicted distribution being multimodal and the peak locates in a run mode. Additionally, we also found state-of-the-art have close-to-fine outputs, namely, they predict heat maps at different resolutions. Based on those observations, we will propose a large self-distillation-based method to adapt the model to new areas. For large self-distillation, we use a pre-trained model from another area as a teacher model to generate pseudo labels for images collected in the target area to supervise the student model, which initialized as a copy of the teacher. Since teacher's output can have small positional noise and large outliers, we then propose solutions to address those. For the small positional noise, we propose to use teacher's high-resolution output to supervise the low-resolution outputs of the student, as high-resolution outputs are usually more accurate, and the downsample them to a lower resolution suppresses their positional noise. Besides, when the output is multimodal as shown here, we select only the max mode to generate the pseudo ground truth. This can prevent the uncertainty in teachers' predictions from propagating to the student. However, what if there are multiple equally likely modes in teacher's prediction? In this case, selecting the peak might select the run mode, resulting in training the student with a large outlier. We observe that for samples with multiple equally likely modes, the teacher and the trained student can have their predicted locations on different modes, as shown in the figure. Unlike purely categorical tasks like image classification, the classes in the heat map, namely the pixels, have spatial orders. Therefore, we propose to use a first trained student model as an auxiliary student model and measure the distance between teachers and the students' predicted locations as a criterion for outlier detection. Finally, we select samples with more consistent predictions to train our final student model. Here is an overview of our proposed method. It has two steps. In step 1, as shown in blue, we first train an auxiliary student model by supervising its low-resolution output using the peak mode in teacher's high-resolution output. We then use the auxiliary student model for outlier detection. In step 2 training, we train the final student model with filtered data. We tested our approach on two state-of-the-art methods, and it shows consistent and considerable improvements on two benchmarks. Here we show some qualitative results. In the first example, the student model learns to better disambiguate similar locations. In the second example, even though the teacher model does not pick up the correct location, the student model learns to explore this location. Please find more details and results in our paper, and thank you for your attention.